Let's talk about types of waves and reflection. And as much as I would love to find a cool YouTube video, I think it would take longer. And so I figured that this is the quickest way to get through stuff so we can get on to the more interesting things here. And we could talk about the types of waves. And generally the two types of waves that we're referring to here are either compressional waves, also called longitudinal waves, and transverse waves. We're going to change from capital to small case. So you have those are the two general types of waves, but you might have been thinking of, for example, light waves or sound waves or water waves. There's surface waves, earthquake waves. There's all sorts of waves that we can talk about. These are the two basic kinds that we generally talk about, and so we need to know these. And the reason is because compressional waves have to do with sound, and then somewhat transverse waves are more appropriate to discuss light. Both can be used in some in different situations. There's overlap, okay? So it's not strictly one type of wave for one type of method like light and sound. All right, let's talk about the more common version, I guess you could say. And a lot of times you would probably call this the water waves, but this is the one we talked about before. This is a transverse wave, okay? But this isn't just some kind of wiggly rope. This is dynamic, okay? And the point is that when we add energy here, then it transmits through the medium. And let's put a barrier here, because that's going to be important later on. Excuse me, that there's a barium. Okay. What we see is that as this thing flaps up and down, back and forth, right? You're over here causing this to move up and down with a certain frequency. And at any given moment, though, this then inverts. We're not going to draw every single one, right? But then you get that. In other words, peaks become troughs, and a trough becomes a peak or a crest. And so it keeps going back and forth. And so that concept is very important to us, because what happens is if we put a little piece of string right here, we just tie a little piece of string here, flapping in the breeze. What happens is, right, the string will go down here, and what we find out is that that particle, right, represented by that string, is actually in motion in a linear direction. In other words, while the wave appears that it is going toward the block, towards the barrier, it really isn't, in the sense that this particle here, if we look closely, we could sit in class and we could watch how it was only going up and down, right? So this particle here is only going up and down. That's really all that's happening here. So while it looks as though this is progressing to the right, actually the particles are moving perpendicular. So in a transverse wave, right, particle motion is perpendicular to what we call propagation. You should really learn that one. Particle motion is perpendicular to propagation. All we're really saying is that the wave moves this way, right? But the particles move this way. That's all that really tells us, is that a transverse wave is described by that type of motion. Okay. Now this is true for water waves in some sense. Not totally, though. It looks like water waves would do this, but they actually do something else. So there's your transverse waves. Not much else we have to talk about there. Then we can talk about the longitudinal. And that is more like a slinky. So what I want you to draw, we call it transverse. I'm sorry, longitudinal. Also known as compressional, which makes sense because when we talk about slinkies, that's going to be very helpful. Can't handle that. Got to get rid of that. Okay, so longitudinal or compressional waves, that's basically your slinky. So what I want you to draw is 3 or 4 coils there. Let's draw 4. Okay. And they're going to be a certain spacing apart. And then we're going to open that up. 1, 2, right. And then you compress it again. And so we'll draw one more. 1, 2, 3, 4. Now this is interesting, especially when you consider that a transverse wave was more symmetrical or more consistent. But what we have here now is an interesting way to look at wavelength. And we could really say that the wavelength here still stands, that we go from one portion of a wave to the next identical portion of the wave. So that could be a wavelength, or we could go from the end of this coil, right, to the end of this coil. So they're going to be consistent. That's the wavelength here. And it makes sense why this is called compressional waves. And I should have allowed some room here, but this is called the compression. And that's going to be very important with sound. And then this is called the rarefaction. Not rarefaction, but rarefaction. You could remember it as a rarefaction, I guess, because it's seldom that kids like fractions, so it's rare. So rarefaction, but that's an opening up. And there's a phrase called rarefied air. Okay, that often happens when there's quiet in the conversation, right? So you can say, well, the air became rarefied. What that means is that there's nothingness, there's opened space. Okay, and so that's the concept of rarefied, is that this is opening up and there's space. Obviously, compression is squeezed together. Okay, but what happens now is if you follow particle motion, let's put a piece of string here on this part of the coil, and we can set it down here. So there's your little piece of string that's on the slinky or the coil or whatever. It moves in this direction, and then it moves back. And so pretty simply then, we say that the for a longitudinal motion, the longitudinal waves then is particle motion is parallel to propagation. In other words, if the wave is going one way, then the particles that comprise that are also going that way, but this time they're going back and forth. Okay, so this is the particle motion. Okay, so those are the two basic types of waves, and we can talk more about water waves, earthquake waves, and so on. I think we'll find a video that does a much better job, or an animation anyway, but those are the two basic types of waves. I will list some other things here first before we go on to the concept of reflection. Okay. If we talk about wave types, not just classifications, but we could talk about water waves. And water waves are really a blend of a couple kinds, and we'll talk more about that later. And there tends to be somewhat of a circular motion, actually, that part of the water has this kind of circular motion. You'll see that in the video later. There are what we call surface waves, okay? And those are generally associated with earthquakes, okay? That this entire surface here might be like a blanket, for example, okay? Draw a little thickness in there, okay? But there's some kind of motion that is very specific only to surfaces like land or blankets, for example, that are different from water. And so those are just a couple examples of different ways. We could talk about gravitational waves and so on, but I guess we could talk about light waves. And they are unique. Now, they have transverse wave properties, okay, but there's no medium, okay? There's no medium, but really they do display transverse wave properties. And then finally we could talk about sound waves. Now, those are compressional waves, longitudinal, right? But light waves and sound waves are different. You need a medium for sound. It requires a medium. You must have something carrying that wave. So light waves don't necessarily need a medium, but they could use one. They could go through water or glass or plastic, for example. Okay, sound waves need some kind of stuff to work. Okay, so those are the concepts of waves, but now what we should talk about, which is going to be very relevant in sound and light concepts, is the concept of reflection. And it's not going to be quite what you think it is. We're going to have a video later on about this, but let's take our standard support here. And so we'll draw a block of wood with a hook. And we're going to have a string here. But this time I'm going to put what's called a wavelet. Right? That's a portion of a wave. So situation number one, that wavelet is propagating here. And what's going to happen then is as it propagates, it reaches this fixed barrier. And so this is called a rigid barrier or rigid support. And what's interesting is that it continues on, continues on. It reflects inverted. It inverts, it flips over. Okay? We'll talk more about what that means later on when we talk about superposition. Okay, but when and that's going to be important now when we talk about superposition and sound waves and so on. So we could call this plus A, we could call this minus A. And that way we give some directionality. Okay? If we take this wave, however, and we put it on a open barrier, right? Now we're just going to put it on some kind of a metal ring here. So we'll take this rope here. Again, we'll put a wavelet there. And then it has a loose barrier. Right? It's not rigid. What actually happens is that as the wave propagates this way, it strikes this barrier of sorts, but it returns upright. After reflection, it's upright. Okay? And so it does not invert. And that's going to be very important when we talk about light waves and how they behave. So the returned wave is upright or erect. Okay? It returns in the upright direction. Now, the slow motion version of this is very interesting, but we're not going to talk about that for us. We might look at it, but we don't need to know all of the little phases that go on with those kind of behaviors. Okay? But now if we talk about superposition, right? If we talk about waves that are going to be on top of each other. In other words, they're going to be in the same place at the same time. This time we're not going to have a barrier, but instead we're going to progress these waves toward each other. All right, so these two wavelets are going to come together. And what we'll see is that you get what is called the algebraic sum of the two waves. Now, we could call this plus A and plus B, right? And so you would get A plus B here. Okay? And that is called constructive interference. Close. Let's call it interference. That's a T. So when they combine, they have what is called constructive interference. But now we should continue because something else happens. And that is that they pass through each other as though the other one did not exist. And so A continues on its path, B continues on its path. And so it is though nothing happened here. So non-interference. Unaffected. Okay. If we go back here, this is when they are superimposed. Superpositioning, super to be on top, position, place, on top of place. So those two, that is the superposition or the interference, right? And so you could say, well, now they acted as though neither one existed. So they pass right through each other, and sound waves do that too. We'll talk about that later probably. But we could also talk about how you have a different kind of interference. Obviously, if this is constructive, then the next one's going to be destructive interference. And it starts with a wave here, and we'll take the algebraic or same magnitude but different direction. Okay, so if this is case 1, this is case 2. So the waves are propagating towards each other because that's what waves do. And they come towards each other, and we could call one a plus A, and we could call this a minus A. When they interfere or are superimposed, then the combination of them actually is here, and there's nothingness there. Right? Well, this is positive A plus the negative A. That equals 0. So there's no displacement of that medium. And so this actually happens with slinkies and ropes and your noise canceling headphones. They can actually cancel each other out. That's how this works. Afterward, however, then you would have the negative A here and the positive A here, so that they have traveled through each other. Okay? So the idea is that now you have what is called destructive interference. The idea is that the combination of those resulted in something that doesn't exist here. These two concepts here, by the way, constructive and destructive interference, we will see these again when it comes to sound waves, because that's actually going to be a very important concept. So those are just the basic ideas, but we need them as we progress towards sound and light here. The idea is that there are two main types of waves, compressional and transverse. They're described by the propagation and the particle motion. So transverse particle motion is perpendicular. For longitudinal, then the particle motion is parallel or in line with the propagation, so it goes in the same direction here. And then this concept of rarefaction is that opening that happens behind a wave here. Okay, so as this compressional wave or slinky gets squished, then we'll see that opening happen behind. There are really other types of waves that are combinations of transverse and compressional, and there's some circular motion. So these are other types of waves that we're not going to get into with this lecture. But one of the more important concepts is this wave behavior of reflection and the concept of rigid or loose barriers. And so a fixed rigid barrier here, the reflection is inverted. That's certainly going to play effect when we do sound waves. And then here we have an upright return. Okay? And then finally this concept of superposition has to do with what happens when waves come together. They actually behave as though they pass through each other undisturbed, but at the moment they are superimposed or superposition occurs, then we get the algebraic sum. And so if they add up together, we get constructive interference, and if they cancel out, then we call that destructive interference. So that's just a general idea of waves and reflection.